Hello, this is John OT. In this part of the Ultra Recording Simulator tutorial, we will continue with the design of part 1 and in the process introduce you some advanced design concepts and useful productivity tools. Here is the current state of our design from part 1. This is the result of calculating the writing of perpendicular media using a single pole write head. Under the root node, let us reset the magnetization states of the design by clicking this button. There we have it. Next, let us pattern the storage media into a custom shape. We will use the so-called Salida utility for this. Salida is a standalone array patterning utility that can be invoked from within macOS software products. A separate tutorial discusses Salida in detail. In URS, we launch it from the Tools menu. Here we have Salida loading. It is completely loaded now. A geometric map of our media that we can interact with is displayed in this box. We will use a mask image to pattern our component. We select mask here. We click this button to select a mask file. We first reset the pattern by checking the clear box here and clicking all. There. We apply the mask by clicking this button. There. We conclude by transferring the shape to our URS session by clicking this button. Let us close Salida. And here, back at URS, we can see that the storage media has the new custom pattern. In the URS window, we have a lot of latitude to tailor media material properties to our liking. Through the Tools menu, we have access to other very useful utilities. These are the Magomat utility and the MagJob utility. The Magomat utility allows the specification of local variations of magnetic anisotropy and initial magnetization directions for a sample. MagJob allows the submission, monitoring, and management of background calculation jobs. These are standalone utilities that can be invoked from within macOS software products. Separate tutorials discuss these utilities in detail. Let us include an underlayer in our design. This component is a magnetic shield underlayer. As you can see from the Materials tab, the shield is characterized by magnetization and relative permeability. Shield surfaces are modeled using rectangular meshes that are used in the calculation of induced surface charge distributions. The component size and mesh dimensions are specified under the Geometry tab. We will now run a calculation for this design, and we will record the calculation. Keep in mind that we are referring here to the storing of the system solution states, not to technical recording in magnetic data storage systems, exemplified by our writing simulation schema. Simulation recording is carried out using the controls in the input area of the recording and playback node. We prepare for recording by clicking this button. Its color changes to red, an indication that any calculation will now be recorded. Let us go ahead and click the Run button. I will skip ahead and continue the narration after the calculation ends. The calculation is now done. Let us take a look at some of the playback functionalities. Here in the playback frame, we can click the Replay Forward button, this one, to play back the stored solution states in their normal sequence. Clicking the Replay Reverse button next to it replays the calculation in the reverse sequence. With the Auto Repeat option selected, pressing any of these buttons will continually replay the recordings forward and backwards. Let us do that as we look at the various parts of the solution. Here we go. Note how the computed states are played back both in the System View box and in the curve windows. Let us pause the playback briefly. Right-clicking the mouse in the plot window displays a shortcut menu for working with the plot in many ways. This includes transforming the plot into other useful data. Standard mouse sweeping actions allow zooming into any part of the plot. Double-clicking the window restores the unzoomed view. In the System View window, let us right-click the storage medium and let us select Vector Map from the shortcut menu. Here's the Vector Map window. All the tools that are needed to navigate all sections of the vector map are available in this dialog box. Right-clicking the mouse in the map box displays the shortcut menu for working with the map in different ways. This includes generating the vector maps of several interesting physical quantities, as well as accomplishing various differential vector transformations of maps. Standard mouse sweeping actions allow us to zoom into any part of the map Double-clicking restores the unzoomed view. Similarly, we can bring up the shield charge map of the underlayer from a shortcut menu. There. This dialog box allows us to view the charge map of all active faces of the underlayer. This window has similar functionalities as the vector map window. Let us resume the playback of the recording. The map window is refreshed continually during the playback, and so is the vector map window. Okay, we can stop the solution replays now. Let us jump to the starting state of the computation, and let us save the design to file. There. Finally, let us take a look at a pre-computed writing simulation example that illustrates the so-called heat-assisted magnetic recording or hammer. There we have it. Attached to the main pole of the single pole head is the stem of a thermal source. During the writing of a bit, the thermal source heats up a portion of the media in a thermal footprint region contained within this red rectangle. The thermal source geometry and characteristics and the geometry of its footprint are specified under the thermal source node. Let us replay this calculation. Here we go. The footprint moves with the right head. This is the temperature profile of the thermal source in the footprint region. It switches in step with the MMF plotted here. And this plot is a cross-track magnetization profile. And with that, we come to the end of part 2 of the URS tutorial. Here is a recap of what we learned here and a preview of things to come in part 3. Thank you.